Alrighty, welcome back, or welcome to, depending on whether you were here just now or have just come in. Our next talk in this room is From Chaos to Zen, Lessons Learned from Developing User-Friendly APIs. Our speaker is Stefan van der Merwe, who is an electronic engineer by training, a software engineer by job title, and an open source software geek by all other standards. You are effectively describing me. Stefan discovered his passion for empowering people at Xmente Technologies through the extensive use of Python to manage infrastructure, develop software tools for use in thermochemistry, at which point you're no longer describing me, and automate mundane administrative tasks. I understand what the word thermochemistry means, but beyond that, no, I've got nothing. But Stefan clearly does, so we're going to change the topic and you're going to spend 45 minutes telling us about thermochemistry. No. Okay.
Yes.
Please no. Okay. Let's go with the API talk instead. We're going to have a talk from chaos to Zen, lessons learned developing user-friendly APIs. Stefan, take us away.
Thank you, Kim. I really appreciate your enthusiasm when you introduce us. Right, so welcome, and welcome to this journey with me where I hope you'll learn a thing or two about crafting user-friendly Python package APIs, or at least have a good time listening to my voice. Right, so who am I? My name is Stefan van der Merwe, and I'm an electronic engineer turned pyrometallurgical software sorcerer. My main task every day is to capture the incantations of our pyrometallurgical alchemists into spellbooks of code that we can share so that we can share our magic with the world. I also carry the responsibility of ensuring that our team has the correct set of tools to make the magic happen. Two of my personal favorite tools that I use regularly are Ansible and Typer, though today is not about that. So, I believe APIs are the unsung heroes of the software development community. But what is an API? An API, or application programming interface, is a set of rules and protocols that allows different software applications to communicate with each other. It is like a restaurant menu. It tells you what you can order without you needing to know how the kitchen works, or in this case, the code. It is important to note that APIs are not limited to web. Seems like I'm breaking all of the mics today. All right, you will find that APIs come in various flavors. Depending on the resource that you use, you will see that they are generally categorized anywhere from 3 to more than 5 categories, like web, library, operating system, hardware, and third-party APIs. Our focus today is not on web APIs. Sorry guys, this is not an epic showdown of web APIs. And yes, I do consider REST and GraphQL as protocols, not types of API. If you were expecting a condensed version of the first 2 pages of a Google search for different types of API, sorry, that's not it. We are exploring Python package APIs, the interface to your Python package, that which your users will see. I am going to strap today's talk on the back of a package called ChemAppPy. During this journey today, we're going to have a little look at Xmente's journey with a library called ChemApp, ChemApp itself, our love affair with Python. Then we'll meet the star of our show, ChemAppPy, before we discuss some pitfalls that we have identified in our adventures with Python package API development, as well as then unveiling what we consider good design principles. Who is Xmente? We are a pyrometallurgical engineering consultancy firm that helps our clients to advance through insight. We believe that by truly caring for your clients and their needs, applying fundamental scientific principles, and using the latest technology, you can gain valuable insight into their thermochemical processes and help them to make more informed decisions. We've been using ChemApp which is a thermodynamic library for decades to help us gain this insight. A little bit about ChemApp. It's a thermodynamic library, and it's the brainchild of Gunnar Eriksson. It is developed by GTT Technologies in Germany, and it has become one of our greatest allies in understanding or gaining more understanding into pyrometallurgical processes. But the power of ChemApp is locked away behind something called interface. Am I dropping out again? Okay, sorry guys. So it's locked away behind something called a TQ interface, which is the bridge to the thermodynamic realm. Right, a little bit about the TQ interface. We're taking a long walk here, sorry guys. It is something that's delivered to us by the CalFat group. The CalFat group stands for Calculation of Phase Diagrams, is an international group of scientists and engineers that have been working together since the early 1970s to develop thermodynamic database and software standards. They've done a truly fantastic job to add computational to thermochemistry during an era when a computer was the size of a room and had less processing power than your pocket calculator. One of the fruits of their labor is this TQ interface and its constraint to the languages that it was used on and the hardware that was available. Spoiler alert, the TQ interface is not user-friendly. Fast forward to about 2013, and Xmente discovers Python and its usefulness for the first time. It was truly love at first bite. Wink, wink. We were amazed by how easy it was to learn and how quickly we could develop software in it. Python was the perfect tool for our team of engineers who were not programmers to develop scripts and perform multiple complex calculations. It is reasonable for us, or we consider it reasonable, to expect from a chemical, mechanical, or metallurgical engineer to learn Python. We do not consider it reasonable for them to have to learn Fortran or C just to be able to work with a library. Finally, ChemApp shows up. So, if your favorite library does not speak Python, what do? Well, you teach it some Python. Using a little known, I don't know if it's that known, package called Python, you probably might have heard about it, we were able to load the ChemApp C library into a Python environment so that we can work with it. Right, so I want to talk a little bit about the evolution of ChemApp. The first thing that we will consider is that there were three major milestones along its journey. The first is developing a very simple wrapper, simply exposing what is available in ChemApp in Python. Next, we had a more basic wrapper. It's something that we call a basic wrapper that we have added some functionality to it so that it makes the development cognitive load on the user a little bit less. And then finally, we arrived at something we call a friendly API or wrapper, and we consider it to be user-friendly. We'll do this by taking a look at a scenario or an example which is from the ChemApp documentation, stripped down to the minimum that I could. And then in this example, we'll have to perform a few steps. Firstly, we'll initialize the ChemApp library. Next, we'll load some thermochemical data. Then we'll display the system units that ChemApp is using at this moment, set some conditions for the equilibrium calculation, and then perform the calculation. I have to add some disclaimers. All of the technology that I'm talking about is proprietary. ChemApp is a proprietary library. ChemApp as a commercial proprietary library was superseded by ChemApp for Python and EM Thermo a couple of years ago. However, the usage of ChemApp is still a very good vessel for me to explain the journey that we have gone through. Okay, well, that's smaller than I hoped it would be. Anyway, so this is just a quick look at how the examples are going to be structured that we're looking at. We have adopted a default script layout in Xmente where we make use of the if dunder name equals dunder main block to ensure that our scripts can be imported without running through the main process. We make a lot of use of Sphinx autodoc, and your scripts will be executed if you do not have this block of code in it. So Chemap is a Fortran library containing many subroutines exposed through the TQ interface. For the first simple wrapper, we only expose the TQ interface as it is. This is not the Pythonic way. I realize that. But it's the easiest way that we could get started. The first thing that we did is we created a function called abort. Let's see if we can enable a laser here. We've got a little function here called abort program. This is to follow the exact same methodology that Chemap uses in their documentation for their C and Fortran examples. Before any calls can be made to the Chemap library, we have to initialize it. This is what we do with the TQ-ini subroutine or method. After each call to the Chemap library, an error number is returned. You then have to check that error number manually to ensure that an error did not occur. If the call executed successfully, a 0 will be returned. Otherwise, the error code will be returned. You can then check the Chemap manual to see what that error code means. Not very user-friendly. We will then just simply print out the version of Chemap that we're using. This is just to ensure that our little program works. I would like to just draw your attention to every single if statement that we have to make after every call to the library, just to check those errors before we can continue on to the next one. To load data into the thermochemical library is a multi-step process. First of all, we need to find a Fortran unit that it uses, that it has to load against. Next, we have to actually open up the file. Thirdly, we read the file. And then finally, we close the file. Now your data is available in the thermochemical library. A common error that we see emerge in our process engineering department is that the guys do not ensure their system units are read correctly. Okay, what I just wanted to show here is that to retrieve the system units that are currently set in the Chemap library, we can use the TQGSU or get system unit subroutine call. You'll see that for every string that I pass through to a method or call, I have to encode it. This is to ensure that it is a byte string when it goes to the C library, as it cannot interpret a Python string. Next, we'll set some equilibrium conditions, show what the current settings are, and then perform the calculation itself. Okay, that was quite a mouthful. What is it that I just showed you? First of all, I believe it's not user-friendly. After every single call to a library, to then do a trivial error handling, it's a little bit clunky. Then I do not believe that writing code like this can be considered Pythonic at all, and it's definitely not user-friendly. What can we do about this? Cool, let's have a look. First of all, we'll move the error handling within the Python package itself. Over here, we can now see that we can make a call directly to the library without needing to capture an error code and handling that. So don't load that cognitive load of handling those error codes onto your users. Handle it within your package. We could also lose the abort program function, as all of that functionality is now captured in the package. Next up, you'll see that we can, instead of passing a string to our method call, we will then rather use an enum. Now, I know if you can see that clearly, and the keen-eyed among you might have noticed that there's no syntax highlighting on these packages. This is a dinosaur that I dug up to do this presentation today. We do not maintain stubs for these files. So if you have stub files for your API or you've written it in your package in pure Python, your most modern IDEs will be able to use IntelliSense to syntax highlight and to actually autocomplete and predict some of the methods and values that come out of it. Once again, for the system units, we just use enum options. The reason we chose to do this is we restrict the values that our users can send into the library. Instead of having to compare a lot of string values, you provide your user with a list of available options through an enum. Okay, so we've got a little bit better error handling. We don't have to check our code every single time that it returns a call. It's still not truly user-friendly. We've still got these TQ, CEL kinds of endpoints, which in this case would have meant TQ, calculate equilibrium, list results. Mouthful. I see some opportunities here. We can provide some friendly names for our methods. We can group related methods together. We can reduce the number of method calls that are necessary for functions or for performing actions that require multiple calls to our Python package. For instance, loading a thermochemical data set, in this case, requires 4 calls to our library. This is what our friendly wrapper started looking like. At the top, you'll see that we've got 4 classes that we are importing. We've grouped our related or methods that relate to each other together. It makes it a lot easier when you only have to search through a small number of calls, because there are 77 of these TQ calls. So if you can group them together in related methods, it makes it a lot easier to find what you are looking for and to work with it. We are trying to enable our users of this package to have a conversation with the package, and through the powers of something like IntelliSense, using friendly methods, that becomes possible. You'll see that our method call to get the version number has changed to get version number. It's very explicit. No more remembering TQVERS. Another thing that you'll note is that there's no more need for us to call TQINI. In the friendly wrapper, we initialize the library, the ChemApp library itself, upon instantiate, once a ChemApp class is instantiated. Over here, you'll see that through the powers of IntelliSense and prediction, we can, for our information class, see that we can get array sizes from our package, the copyright message, dongle information, expiration dates, to get similar information directly from the shorter TQ interface you would have used, TQNSIZ, TQCPRT, TQGTHI, and TQGTED. Ooh, a lot to remember. The first time that I used it, I had to sit with the manual open next to me the entire time. Over here, you'll see that when we load data, it's a single method call. No more making 4 calls to simply load our data into our system. When we display the system units, we do not have a single endpoint, but rather we've replaced the single method call that we made to display the unit, passing into it an option variable with a single method that takes no arguments, but it already describes what you are getting. In this case, we are using the abbreviations PVTE, which is standard abbreviations in the pyrometallurgical industry for pressure, volume, temperature, and energy. I would like to point out that at this point in time, we are overhauling all of our main APIs, and we have decided to move to a more explicit naming. So these methods will most probably change to something like get pressure unit. It's a longer method call, but it's explicit. And you won't get into an issue where, for instance, with temperature, if you used temp, you confuse it with a temporary value. This is just to show how our code reduces from a very simple wrapper with very basic API calls to something where we handle more stuff in our package and to a very, or not very, but at least a friendlier API to our package. So what are the common pitfalls that we have identified through our years and our journeys of developing Python packages? Inconsistent naming, overly simple endpoints, overly complex endpoints, inconsistent return types, and lack of documentation. You would note that some of the pitfalls that I mentioned are not covered by the examples that I have shown thus far. Let's take a quick look at inconsistent naming. We're back into the TQ namespace. At the top, we want to get the name of something, let's say a system component. The endpoint will be TQ GNSC, which is get name system component. For phase, it's TQ GNP, get name phase. All right, I was busy working with this, and then next I thought, cool, I want to get the model name. TQ GN, nope. To get the model name, it's TQ MODL. All of a sudden, the pattern is broken. If you name your variables, use consistent patterns. Otherwise, you will start confusing your users. In our example, we used what's shown in the bottom. We had to make 4 calls to our library just to load data. We replaced that with a single load call. If you develop a package and in your API you have simple methods that return results that you usually group together and use together, I would advise you to either group them together or to provide convenience methods that perform those steps for you. Otherwise, your user's code becomes cluttered with repeated sets of calls to your API or your Python package. Over here, I show an example. This is a method that we didn't show in our examples earlier, but the TQGETR or get result method can become really complex. So this is a single method that can retrieve data in various forms, and then the return type will also differ depending on what type of data you request it to return. It is the user's responsibility in the Chem app documentation to, when they call TQGETR and set a certain state variable option, ensure that the index number is greater than 0 and the constituent index number is greater than 0, or that it is less than 0 depending on the state variable option that you requested. What we do with this is we break it down into more methods, with each method saying explicitly, okay, get result IA, incoming amount. And then we already set the index for the phase and for the constituent so that the user does not have to worry about that. We make it more accessible to the user. That also allows us to, for each method, type annotate it with a correct return type. You won't expect it to return something like a list and then all of a sudden it returns a single float variable. So what do we consider the secret sauce to recipe? Secret sauce recipe to crafting user-friendly Python package APIs. It's something we call empathy-driven API design. Okay, but what does that mean? One and only one thing: to care about the developers that use your Python package. If you truly care about them, you will design your package in such a way that it's easy and friendly to use. What follows are some of the principles that we have adopted to help us craft our Python packages. Be warned that these are extremely opinionated and that you might not agree with all of them, if any. When you name your methods, use verbs. It's an action, something that you're performing. Use nouns for properties. Be consistent in your naming. If you start to use something like get temperature, do not all of a sudden change to volume get. Be consistent in your patterns. Explicit is better than implicit. I've already mentioned the example, but get temperature instead of get tea. Remember that documentation is like a GPS for your developers. It helps them to navigate through your Python package API. Document your package. Make sure that it states why it exists, what it does, and how to get started for a new user. Include examples. We prefer to also include our API endpoints in our documentation. I've already mentioned Sphinx. We use Sphinx Autodoc extensively. Ensure that your doc strings, if you use a tool such as Sphinx, ensure that your doc strings contain what the endpoint does, explain what parameters it takes, and what it returns. Type annotations can get you a long way if you use it for that. When it comes to error handling, we tend to prefer to raise exceptions, not return error code numbers. We would rather have our system talk to the user than to return a number that he has to go look up manually. When possible, use standard Python API exceptions. Where not possible, and where you create custom exceptions, make sure that you inherit from the standard Python API exceptions and that they are meaningful. A Python package API should be sleek, not clunky. How about only exposing the endpoints that are useful to your users? Only expose those methods and functions that you want your users to use. You can explicitly control these, the visibility of these, by using the dunder all in your dunder init py file. This allows you to build large packages with many endpoints without overwhelming your users with endpoints they were never meant to see. Also consider grouping related endpoints into classes or modules. I would advise you to think like the developers using your Python packages. Walk in their shoes. If possible, try to use your own package as a user would. Where you find it difficult to place yourself in their shoes, ensure that you have proper communication channels set up so that you can get feedback from them. In summary, I would advise you to use consistent naming with meaning. Write the fantastic manual, handle errors gracefully, keep it simple and elegant, and think like a developer. Thanks, guys. Any questions? James, wouldn't expect any less.
I'll take it. Let's give it a try. Okay. So it was James. Where's James? There's James. No, I missed the tall guy.
Yes, I want to know how angry your users were when you were changed API versions from like the old version to the friendlier version. I'm sure it's better, but they've got scripts that are already working, and now it's different.
I don't know if it's on the mixer.
There we go.
Oh, there we go. Thanks for the question, James. So the first time that we actually made this package available for users was once the friendly was finished crafted. So we never ran into that issue, except for the software developers that actually need to build this thing. They obviously ran into the issue. But no, Kmap Pi itself was never commercially available before the friendly existed. Apart from that, we also added on another module which we call tools, which automates a lot of the post-processing that these guys would have done once they have finished a thermochemical calculation. That's also why Kmap Pi was superseded by 2 packages. The tools part is something we keep internal at Xmente when GTT took over the actual Python API to their software. Yes?
I hope you don't mind this. My questions are more so towards the thermochemical calculations.
Great stuff. Something I know very little about.
Okay.
I'll try to answer.
I was just interested because you didn't go much into it at all, as like what do the calculations look like, what actually occurs, what sort of, maybe there's some form of algorithm that's being used. So I was sort of really interested in that. How long does the calculation take? Does it need high performance computing? Those sorts of things. Okay,
I can answer some of those questions.
Okay.
So first of all, the library that we use is called Kmap. I know of 2 other libraries. There's an open source one, OpenCalFat, and then Thermochemica is also a proprietary thermodynamic library. It's an extremely quick and easy and fast calculation if it can reach equilibrium in a short time. So it's the methods that they use, the algorithms that they use, I'm not familiar with. We've got material scientists working at our company. They know that more.
I was in the field.
You were in the field. Okay, yeah, cool, great.
Non-linear optics.
But if you'd like to know what the algorithms looks like, it's simply a Gibbs-free energy minimizer. That's what it does. If that means enough for you. And if you'd like to know what one of those of those libraries looks like on the inside, I would advise you to actually read the articles by Gunnar Eriksson, as well as to take a look at the OpenCalFat repository on GitHub, because the Fortran code for it is available there. We simply use Kmap Pi because it is the largest, or it's connected to the largest database of thermochemical properties in the world that we are aware of.
Thanks. We do have an online question from India Bongo. Is if you can touch on the part about _all in your _init, I assume. As in, what does that do? I think it's a question that arose, yeah.
Right. So _all, I've used the word dunder. For those who don't know it, that's what it stands for, is double underscore. So double underscore all in the init method, when you import your package, Python takes a look at that all statements, or it takes a look at that init file, and then it creates on the object that it imports. And if you don't specify it explicitly, it creates the all attribute, which is usually, I believe, a dictionary containing the name and the relation to that method of that name. So if you explicitly set that list or that dictionary, then you're telling Python that when you import this package, this is what you can make available to the user.
Yeah. So, I mean, from a simple possible example, if you had a module that had methods in it called A, B, and C, and you put in your all A and B, you cannot import that module and use .c.
Yeah, you can't use .c, yes.
Technically, yes, you can, because you can do anything you want in Python, but you have to leap through some more flaming hoops to do it. Yeah.
Yes.
Awesome. Do we have any more questions in the room, otherwise online? In that case, I did think of one comment I was going to make, and because I have the microphone, I get to make those comments. Your point about documentation being like a GPS was an excellent one. It did strike me, though, that the other thing that means is much like a GPS. If your documentation is wrong, you can be sent off a cliff.
Definitely.
Oh, done. Mohammed. Sheena, you pointing out Mohammed? Yeah.
Hi there. Thanks for the talk. I just had a question about debugging.
Yes.
And like, how often do users run into issues where they have to debug it, and then how do you kind of lighten them with which level the error is on, like if it's on the chem app or in the API usage?
Yeah. So in this specific example, debugging can become a real pain, real fast, because first of all, it's Python code. It's not pure Python. So stepping into it is tricky at best. And this, as soon as you hand off data or a call to the library, with the Fortran library, you have no control over it anymore. So using something like the GNU debugger, I can actually see if it broke in my Python code, in my Python code beforehand. Well, that's easy. Python usually, from the stack trace, you can trace it back to there. But as soon as I determine that it's in the shared objects that it's breaking, then I have to raise that question to the suppliers in Germany and call them and say, hey, guys, we've got a problem. Your library isn't doing what it's supposed to be doing. So it's a real pain. Debugging is a real pain. I would stick to pure Python or something that supports proper debugging. Yeah, debugging is a pain with this specific project.
Well, thanks, Stefan. Another question online. Gordon Ings has asked us. Well, first of all, he said, thanks for a great talk, which I have a few comments of that have been. It was so cool to hear this familiar work described in a domain I have no understanding of, says Gordon. But your message of user empathy was universal, he points out. Do you mind describing your process for soliciting feedback from devs a bit more?
Soliciting feedback from devs. Well, in our perspective, our devs are process engineers. They are most likely chemical or metallurgical engineers that use these scripts to run, or they write scripts where they use ChemAppPy to run multiple, tens of thousands of calculations on a cluster, retrieve that information, and then post-process it. Soliciting feedback from them, I actually initially got to a point when I started working at Xmente where I would sit down with these guys every 3 months and then review what they're doing, see how they're using the application. And that was just because those engineers, or these engineers that use the package the most, are also young engineers and also new to the company. So it was a learning experience for the both of us, for me and these guys, to be able to go and sit down and to see how they write their code, and then ask them, why did you do this? Why did you not do that? That's the way that I do it. I'm in a very fortunate position where we are a small company. I've got more servers running than employees at the company. So I'm in a very fortunate position where I can sit down with these people and ask them, what are you doing? And review their code and see what's going on.
Awesome. Thanks, Stefan. I think we'll call it there unless there are any further pressing questions. Other than to say, Stefan, brilliant. Thank you very much.
Right. Thank you, everybody. Just the last point, remember, your Python package API today might make someone's coding journey easier tomorrow. And yes, we are hiring.
But only thermochemical engineers.
No, software engineers.
I'm kidding.
Software engineers.
This is not the forum to show up and try and get a thermochemical engineer to join you.
No. I'm looking for software engineers and developers.
Awesome.
Awesome.
Thank you, Stefan.
Thanks, guys.